Okay, let's commence with work example 29. Okay, in this work example 29, we want to actually establish that the function absolute value of sine x is continuous on the entire real line. So in this case, you now write down two functions. One is your say gx. You define a gx as the modulus function, and then your sine x as your hx. In this particular case, both are continuous on the real line, and the range of h, right, is a subset of domain of G. This is a condition required to establish that this composition exists. For G not h to be a function, right? For it to be a function, the condition is that the range of one must be within the domain of the other. So in this case, it is true that the range of h is actually the subset of domain of G, and hence this function exists. Okay, so by the earlier result, okay, this result. Okay, so this result says if these two conditions are satisfied, then the composition is continuous at the point A. So we apply this theorem for every point on the real line, and for every point on the real line, these two conditions are satisfied, and for the reason, right? Therefore, therefore G of hx will be continuous on the entire real line, and therefore we have this conclusion that f is continuous on the entire real line. Right, so this to make use of an earlier result. Okay. Right, that is what example 29. Okay, now let's talk about discontinuity. Okay, let's talk about discontinuity. Okay, in the case of discontinuity, we actually so-called categorize discontinuities. No? We categorize. The first category of discontinuity is described as removable. Okay, to understand what do you mean by removable, in this case, right? In this case, you have a diagram that shows you that this is a discontinuous function. It is discontinuous at the point x equals to, right? So at this point, it is actually undefined, and therefore there is a brokenness. This discontinuity is described as removable because you can so-called remove the discontinuity by redefining, if you want to, again, by redefining the function value at A. So to remove the discontinuity, you can actually technically redefine the value of the function at x equals A to the values that is given here. So for that reason, this one is described as a removable, right? You can just redefine the function value to make it so-called continuous. So if you have redefined it, then it won't be a unshaded circle, it will be just like that. That's why it's described as removable, because you can patch it up and make it continuous. Another discontinuity is described as so-called the jump discontinuity. This is a case where you experience a jump. Unlike the earlier discontinuity, there's no way for you to join them back and make it continuous. No. So for that reason, actually you can see that there's a jump. So it's described as jump discontinuity. So it's not described as removable. So in the AP exams, right, it is sometimes asked of you, to describe the discontinuity or to pick MCQ choices to see what discontinuity is that. And then the third one is also called the infinite discontinuity, right? And that happens when you have a symptom either side or both sides. Okay. Now let's look at this example 30, and you're asked to describe the kind of discontinuity it has. Okay, let's see. Okay. In example 30, we are given three statements. So first statement says there's a jump discontinuity at x equals to -2. This is x equals -2. Can you see a jump here? So is this statement true? Yep, this is true, right? Okay, let's see the next statement. When x approaches 2, how does fx behave? Mahil, right? I hope I pronounced it correctly. Do you think it is true?
Yes.
Okay, so when x approaches 2, right? When x approaches 2, which is here, the limit on the left and the limit on the right, indeed it is 4. Okay, it's 4. Right. Then the next one, f inverse exists. Let's hear from in front of Katit, in front of Katit. What's your name, please?
Euler.
Yeah, Euler. Right.
I mean, that is the name.
This is famous, no?
Yes.
Okay. Right, Euler, would you tell us, do you think that f inverse exists?
No.
Why doesn't it exist? Because in this case, right, this function f is not 1, 1. So this implies that f inverse does not exist. So therefore, statement 3 is not true. Okay. Nevertheless, let's check this other condition, this other statement. Do you think that f is continuous between -2 and 1? Do you think this second part of the statement is true? Euler, it is. Okay, this second part statement is actually true, but this third part statement is actually false. So for the reason, our answer to this will be 1 and 2. So it's B. Okay, then let's go on to a theorem. Okay, it is commonly abbreviated as, for the simple reason, it is called intermediate value theorem. Okay, what this theorem says is, okay, if you have a function that is continuous on the, it is important that it is continuous on a closed interval, like this. Okay, closed interval, like in this case, right? If I could actually put a shaded circle here to say that it's actually inclusive of this endpoint, and shaded circle here. Okay, so this theorem says if you have a function that is continuous on the closed interval, and then for a value k, right, that is between, let me say, this k value, right, this k value is anywhere between these two numbers. Okay, so it starts out with a point k that is between f and fb. What this theorem basically says is that you can always backtrack to a point c where f of c is equals to k, here, where fc is equals to k. Okay. So this theorem is quite straightforward when you see from the diagram. From the diagram, right, you can see very well that if I take a point K in between, I can always backtrack to a point C here. Right. So this is actually the statement of the IBT. Now, in the event you want to make use of this theorem, right, class, it is required of you, number one, to state the condition. What's the condition needed? Just one condition, that it must be continuous on the closed interval. You must state the condition. Number two, you should state the name of the theorem, you know. There's always a debate, you know, among students, why do we need to state the name of theorem? Because
you know what you're using.
yeah, so that people know that you are using a particular result that is already established before. You know what I mean? So some students just state the condition and they then draw the conclusion. This is not good enough, you know. You want to actually state the condition, followed by the name of theorem, then the correct conclusion. Okay. So let us now look at we're going to look at some examples later. Here's a remark, you know. It must be connected and unbroken for it to be true. Here cited example. If you have a graph that is 1 over x, right? 1 over x graph is certainly not continuous. For such a graph, when it is not continuous, right, you can't possibly try to apply this theorem across from anywhere here to anywhere there. You can't, okay? Because there's a discontinuity. Okay. I am not sure if you have learned about so-called numerical methods before. Have you learned before? Have you learned numerical method before? Now, this theorem is actually sometimes used to so-called locate so-called roots. When we say roots, what do we mean? Say y equals to fx.
Y equals
When we say the roots of an equation means what?
y equals to 0.
It means yeah, numerical method. Some of you learn, is it? Where do you learn, in physics or in math?
Logic.
Physics, yeah. Olympiad students, So supposedly, if you have a function, y equal fx, right? What does the word roots mean to you?
Y equals to 0.
Roots means the value of x that will make y 0. That's the meaning. Okay, roots. So roots basically means the solution to this equation, that fx equals to 0. So when you say the roots of the function, you are basically saying the roots to the equation fx equals 0. Is what it means. Right. So in numerical methods, if you are given a function and the graph looks like this, and you are intending to find so-called the roots here, okay, the root here. So to locate the roots, right? One of the things that we do is to try to roughly locate where the root lies. What do you do? So you take a point on the left, you try to navigate for a point on the left and a point on the right.
It's a case of you trying to ensure its existence before you try finding it.
Okay. You can just do it by trial and error. So you're given a function, right? You're given a function. If you just do by trial and error, and then you chance upon a point A and B such that this result holds true. Like in this diagram I show here, right? F of A is obviously negative, F of B is positive. when that happens, you can be sure of the existence of a root that is between A and B. You will have a root that lies between A and B. This is what this so-called root finding theorem is all about. And this root finding theorem is actually a result of what we had just now, the intermediate value theorem. Why is that so? No? Because if FA and FB is negative, then you can always find a K that's between FA and FB, and you can choose your K to be 0. No? Right. So if FA and FB are negative, the product of FA and FB is negative, certainly 0 will lie between FA and FB. So therefore, by the IVT, we can always say that there is a value C such that f of C will map to K. And this value C, therefore, is the root of the function or the root of the equation. Right. So using the intermediate value theorem, when applied to this scenario, we are able to actually identify where roots lie by chancing upon a pair of numbers FA or A and B such that FA and FB gives you a negative product. Let's say this example again. Suppose a function f is continuous everywhere. Continuous everywhere means continuous on this interval. No? Continuous everywhere means it's continuous over the entire real line. And then you're given these function values. And then now we want to ask now, in which interval does the function have a root? Okay. Let's have the boy behind Tyler.
Brandon.
Huh?
Brandon.
Brandon. Hi, Brandon. Brandon just came back today, first day. Yesterday. Yesterday in class. So you're all fully recovered. It's not COVID. Okay. Yeah.
Yes, I want to ask to do the makeup diagnostic one.
So do you watch the video? That's okay. I think you can watch it at your own leisure. So in this question, right, where do you think roots will lie? Okay, do you think between -1 and -2? Between 0 and 1. So you think it's between 0 and 1 because? Yeah, because you see that over here, right? Over here, f0 is negative and f1 is positive. So you conclude that there must be a root between 0 and 1 is true. Brandon, do you think there are any more? Okay, so you're saying that this also the same thing. This is positive and this is negative. Again, the product is negative, so therefore it's true that there must be some roots between this. Now, it only says that there are roots. It could be more than one, potentially it could be more than one. Any other intervals that you have identified? Okay, between -1 and 0, right? Between -1 and 0. This is f at -1 and this is f at 0. There isn't a change in sign, so to speak. Okay? Both are negative, so the product is not negative. Therefore, there isn't a root. True or false? Okay. Kritik. There might be roots. Yeah, right. So Kritik says even if there could be roots, just that we are not sure. But if there is a change in sign, like the case of f of -2 with f of -1, we are guaranteed the existence of roots. So therefore the answer to 31 is these two. Okay, this is the intermediate value theorem. Okay, can you try this example? As you're trying this example, I want to remind you that we are going to have the graded task 1 on the 27th of January. Today is what? Today is 13, right? 13. Yeah, just that in between there's the Chinese New Year break, you know. Yeah. As you're trying, can I also do some publicity for my event, or your event rather, the Research Congress 2023. Let me ask a quiz question. Which date does it fall on?
Definitely not immediately checking.
Yeah, Arohi, right? Arohi. Which day is Research Congress?
Wait, day or week or day?
The day, the date. Yeah, 1 day too late. It's 15. 15. Okay, it's a Wednesday, 15 February. You saw my email, right, regarding the projects, no? So if you have projects that you want to be graded, you want to actually fill in the particulars in my links, you know? Yep. Okay, so for this question, example 32, right? Okay, earlier on, Kenneth in front of me was trying to prompt me, say, before we even look for the roots of an equation, Kenneth pointed out that we should actually try to establish the existence. It's true, like, it's true. However, for this particular question and for this type of question, we can just do by trial and error first. What do I mean trial and error? No? We just plug in numbers. Just plug in numbers. Wait, let me show you. Okay, just plug in numbers now. I know it's quite painful to plug in numbers, but actually, if you have your calculator, right, your calculator can generate the whole sequence of number quite readily, you know. Okay, here don't have, this 31, here, okay, 32, right, 32, what you can do for 32 is, you can just work out all these numbers now. You can work out all these numbers. If you have a GC, you don't do it manually, you can just key in the function, and then use the GC to publish the values at these numbers now. You don't use GC to do that. If for those who have the GC, you can do an experiment with it, you know. You just key in the function into the graphical mode, and then you just press Ctrl T, a table of values will appear, you know. I'm not sure, yes, sure. So for this question, right, you want to work out the function values from -4 and then you try to identify now where the change of sign take place.
Okay, the answer didn't define what fx is.
Okay, so Kenneth is particular, which is good. Let fx be equals to x cubed minus 15x plus 1. Right. It'd be better off if you have written it like that, you know. I think it could be better off if you have written it like this. Like that. And I can see things better, like -4.
For this, you only need 4 numbers.
1, 2, 3, 4. So it's -3, 19, 23, 19, 23, 15, 1, 15, 1, -13, -13, -21, -17, 5. Okay, so it might be better for you to write them in this manner, and then you written this manner, you can clearly see that there is a change of sign here, there's a change of sign here, and there is a change of sign here, and therefore you are sure that the roots lie, there are roots that lie in the respective intervals, and you will therefore identify that there are 3 intervals that contain roots from this calculation: 1, 2, and 3, you will therefore know that a root line lies between -4 and -3, a root lies between 0 and 1, and a root lies between 3 and 4. So I did not even at first check for so-called existence. I just, and then my values bear out the results. It says, therefore, I am certain that there is at least one root between -4 and -3. There's at least one root between 0 and 1. There's at least one root between 3 and 4. And that has helped me to identify 3 spots where the roots lie. And given that this is of degree 3,
this has a maximum of 3 roots.
Given that this is degree 3, right? We all know that for a polynomial of degree 3, at best it has 3 roots. And in this case, we now can establish confidently that it has 3 real roots. When we say real roots, what do we mean?
None of them lie on the imaginary plane.
Yeah, you're right. Jingwen, what do you mean by real roots? The term real roots. Roots means solution actually, roots means solution. What mean real? It means roots which are, or solutions which are real numbers. And Jingwen, what are real numbers? What are real numbers, Jingwen? Zoe, you're telling your friend real numbers. What are real numbers, Zoe? You're Zoe, right? Yeah. You don't know. Okay. Real numbers basically are numbers on the real number line. Any numbers that we found on the number line, they are called real numbers. That's all. No? Yeah.
Real numbers are imaginary numbers where the coefficient of I is 0.
That is true. That is a feature of a real number. But the definition of real numbers is formally like that. No? All numbers found on the number line. This is the definition of real numbers. Right? So therefore, quite a lot to write. Okay, I know. I'm not sure if you are keen to write so much. Okay, so maybe a bit of time to read and maybe jot down the essentials. As a student myself, at your age group, right? As I'm copying, let me tell the story now. I also dislike copying in class now. I dread. I noticed just now Khatib didn't copy anything at all. I suspect maybe he feels it in his own way, like I suspect. Right, Khatib.
Yes, nothing.
Yeah, I know. I suspect. Yeah. So how did I get by school days? No, I simply borrow my friend's notes and make photocopy. Yeah, that's what I did as a student because I find that I don't have nice handwriting and my notes always doesn't turn out well. So I always borrowed my friend's notes and make copy from it.
For this one, I didn't bother researching every single term within every single interval.
You just zoom into it lah.
I just get like 4 numbers, find that all 3 intervals are all
Right, can also.
Yeah.
So Kenneth says he did not work out so many values. It's okay. Kenneth says he has bionic eyes, he will just zoom in correctly. It's alright, no? It's right. Yeah, you can do that. No?
Just because I'm lazy.
Yeah, you can do that. So if you have the ability to zoom in to the correct spot and find the pair of numbers that works, you have it. I know it's okay. Right. Okay. Yeah, good question.
You should.
I don't think you're right so lengthily, right? So maybe Kai Wen has a way to abbreviate everything. Do you have a way to summarize everything in shorter paragraph? Okay, I'm sure those with a good language, like this morning, they say knowledge is what? Power, right? and
Not
it
only
is
power, but language and power.
and language empowers it. That's very nice, catchy phrase. I quite like it. Yeah. So Kati, when you were gone, we checked your notes. So it's all blank. I mean, I guess you have a way to fill in the gaps. I guess you probably find it too trivial and you think that you can fill in your own way. I'm alright, no, actually, I'm alright. Yeah. But if you want to be very comprehensive about it, this is what you can write, And of course, Kaiwen protested and said it's too long. She wants to be shorter. Yeah. Hopefully, in exams, there won't be questions like this. But actually, AP exams, the solutions typically are quite concise. Typically, of course. Theophilus, you finished copying it, yeah?
Yes.
Or you write it out your own way?
Actually, I finished like the 5 chapters, so before.
Just like Kenneth?
There's only 3 pages left, so I don't think it's that.
Good. Yes, it's quite trivial, first chapter, I agree.
That's very
Even the last page, I was like,
Okay, no worries. Yeah.
Why is my answers not consistent?
Have you done the tutorial?
yes.
Also,
I set question 10 because I started.
Okay, you'll come to it, next week.
I'm slowly switching up.
Okay, I'm going to move on. So, Kurti, if you don't jot down anything, so you will have a way to revise, right? In my time, no such thing as video recording by teacher, no such, because the technology wasn't mature. In my time, it was just hand copy. In fact, in my time, the teacher would come to the class and write the whole notes on the board, letter by letter. No such thing like what your printed notes and fill in the blank, not at the end. Everything was hand copied, and I look up to those friends who can actually copy very nice notes, Yeah, and then you gotta be nice to them, so that they can lend you notes. And you're very clever, you don't borrow from the one same person all the time. You must have a few friends, so rotate around, so that friend don't feel annoyed, Right. Okay, the next thing is so-called the extreme value theorem. Okay, you can read the sentence. I want a short discussion about this. If you have a graph, that's like this, if you have a graph that looks like this, okay, A, and then this lowest point is B. Okay, now. So if your graph look like this, okay, I'm going to ask you this question, what is the absolute minimum value of this graph?
B.
Yeah, the absolute minimum is actually B, How about the absolute maximum?
Does not exist.
Yeah, in this case, does not exist. You don't say it is. You don't imagine it's here. If I draw the line longer now, some people say if this number is like that. Some people say, therefore the absolute maximum is that symbol. It's not. It's not, because at that point, the function is not defined. You see? So for the reason, it's not existing. That is why you will realize that in this extreme value theorem, you will have the condition later on. You'll see that it must be like that, continuous on a closed interval.
I thought bounded also.
Closed bounded, must be bounded also. Right, very good. Closed bounded interval. Right. Okay. So now this paragraph is trying to define to you what is absolute minimum and what is absolute maximum, and you want to understand it from the context that we have just discussed here. Okay, now let's look at some quick check. Oops. The first quick check, it says does f have an absolute extrema? You know how the inverse graph look like for tangent? Tangent inverse graph look like this,
minus into negative 1. Mid and 0.
Okay, so based on the shape of this graph, do you think that it has absolute extrema?
No.
Okay, the answer is no, okay? So you jot down that is no. I thought that this is easier to be seen from a graph that clearly it doesn't have extrema. If you're wondering where is minus pi over 2 in this diagram, this is minus pi over 2. And this is pi over 2. Okay. So the reason is because you don't have any x's that correspond to so-called an extreme value. Don't have. Okay. The next function. Okay. Let's hear from. I forgot his name.
In front of you.
Chen Yan, right? Chen Yan, what do you think about part B? Yes or no? 有没有?
What is gx?
A function, they define a function gx to be this. So for a function that is uniformly 1, do you think that it has absolute extrema? And the answer is, you said yes, right?
Yes.
You did say yes, right?
Math and 1.
Yeah. If you draw the graph, you can see, being a uniform function, the absolute minimum and the absolute maximum are both 1. Okay, now part C. Okay, for part C, they ask the same question, Okay. You want to maybe draw this graph to see whether or not it has or it does not have. Do a sketch of the graph.
Maximum mean yes.
Okay, let's draw the graph. When it's 1, it is 0. Between 0 and 1, it is actually going to be x. Okay, let's hear from Aiden. Aiden, does it have an absolute maximum? For C, part C.
It does not have absolute maximum.
Don't have absolute maximum, but it has absolute. Okay?
Yes.
And the absolute minimum is?
0.
Right. Okay, the next one. Oops, the answer is there. Okay, I let the cat out of the bag. Why let the cat out of the bag? Do you know? Why the phrase?
Let the secret out.
Why does it mean let the secret out? Do you ever wonder?
I think it's something to do with smuggling tax.
Pigs. Do you know the story behind letting the cat out of the bag means to reveal secrets? Okay, you read about it, it's very interesting. Okay, I'm not sure whether my version is correct. The story went this way that a person purportedly wanted to say so-called sell pigs to someone, but instead of selling pigs, he fills the bag with cats. So that's a secret, So you instead of selling pigs to someone who will buy, you sold cats. So when you let the cat out of the bag, the secret is revealed for the reason,
That makes a lot.
That's why when you were young, you never asked why let the cats out of the bag means to reveal a secret. You never wonder. I did wonder. There's another thing that I don't understand. Raining cats and dogs.
true.
Theophila, do you have any? Why?
I just can't try it.
Okay, no worries. Raining cats and dogs means what? Heavy rain, right? I don't know why, no. Okay. Anyway, I've let the cats out the bag. And the answer is no. Okay, let's press on to this theorem. Now, this theorem dictates this, no? That if a function is continuous on a closed bounded interval, it is important that it must be bounded, you know. Right? Must be a closed bounded interval. If a function is continuous on a closed bounded interval, why is it important to say this? No? Like this one, like this, like 5, like that. This interval is closed, but it's not bounded in. No, so this is not counted. So this type no. Okay. So for a function that's continuous on a closed and bounded interval, this theorem, which is also abbreviated as EBT, assures you the existence of the absolute max and min. Okay, so the remarks is to reinforce what I just said, you know. Okay. I must also caution you something, no? While this theorem guarantees you the existence of absolute max and minimum with the condition, right? That doesn't mean that if you do not have these conditions, they don't have absolute max and absolute min, you know. Because in the earlier examples you saw, in those earlier examples, right, you saw that some of this diagram, right? Some of this diagram, they do not satisfy the condition. Like this one, it's not a bounded interval. This one, right? Not a bounded interval, right? The interval we are talking about is from minus infinity to infinity. And likewise, this one also doesn't satisfy the condition that it's continuous, but it still does have an absolute minimum. You know what I mean? So be very careful about this theorem, the EBT. It only promises you that it surely have if the conditions are satisfied, without which, right, it might or might not. Okay. Then there is another theorem says no. Suppose the value the value fc is an absolute extremum of f on a closed bounded interval. Then, okay. Have you seen this word before?
Critical point is.
What is a critical point? Let's investigate. Okay.
Fx equal to 0.
Like this. This is a critical point. Critical point is when, okay, let's hear from someone. Okay, he's checking up on the handphone, kind of. Let's hear from Theophilus. What are critical points? Do you know?
It's one of the two. Whether I'm not sure whether it takes into account does not exist, but I know fx equals to f prime x. I know f prime x equals 0 is one of it, but I don't remember if.
Well, you're right. Cannot be right.
I don't remember if it does not exist counts as critical point.
Yeah.
A critical point does not need to exist.
No. The derivative exists or not. I'm not sure if the derivative has to exist or not. I know if it's 0, I know it is a critical point. I'm just not sure about does not.
Where the gradient is either 0 or undefined. Yeah, right. So these are so-called critical points, right? So what this theorem says is, if these are extremums or extremas, they are either critical points or endpoints, like this. So if you have a graph that's like that, the extrema occurs at the endpoints, right? In this case, this is actually a critical point, this is actually a critical point. Right, that's theorem 1.2. There's another condition about critical point that you need to know. Critical point, by definition, must be so-called interior points. It must also be interior points. Meaning to say, if you have an interval such as this, right, A and B can never be the so-called critical point. Critical point must be interior point. Right. Okay, let's turn over to do example 33. Okay. Okay, in example 33, you are given a piecewise function. Maybe you can spend the next 10 seconds to sketch this graph, to see how the graph looks like. Give us a chance to sketch graph, and then we can compare. Do we have this example? Okay. Let me revise names. This is Kenneth, Jingwen, Zoe, Arahi, Kai Wen. What's her name? Oh, how to pronounce again? Keyue. K-E, K-E-Y-U-E. Keyue. Hi, I hope you have recovered. COVID. Okay, there's a song that goes way, what can't kill you will make you stronger. So I'm sure you must be singing this kind of song at home, when you have COVID,
No.
Okay. Chen Yan, right? Chen Yan. Okay. Chen Yan. I know Kirti, I remember. Kirti is not Raja. Okay, listen. I know for your race, sometimes I get very confused. Sometimes the father's name is in front, sometimes it's behind. I get very confused. Is there a way I can tell? No way. So it's just guess. Yes. Okay, behind Chen Yan is.
Come on, you wrote his name down just now.
Yeah. I don't know. Wen Kai. Oh, no, Wen Kai is there. Sorry. The average of Wen Kai and Kai Wen is. The average, it's like average, Sorry, I forgot your name. Euler, such a famous name. How can I forget Euler? Okay. Our famous mathematician, Euler. Some people pronounce that mathematician name as Euler. Some people pronounce it as Euler. But I think Euler is the one, Okay, so if I draw the graph will look like this. 0. Between 0 and 2, right? This can be like that. And then between -2 and 0 is like that, I believe. Okay. Now, for a piecewise function such as this, right? You can safely say that this part of the function is continuous over the interval from 0 to 2, for sure. Why is it for sure? Because it is a polynomial. Likewise, you can say that the function fx is certainly continuous on this. Oh, sorry, I made I'm trying to say this. Sorry, I made a mistake. You can be sure that it is continuous on this interval as well. So you're very sure that function is continuous over -2 to 0 and 0 to 2 except the point 0. Why I said the point 0? Because at the point 0, it is where the function is defined differently on either side. And when that happens, you want to check for continuity at the point in question. Class, how do you go about it? Keyue, do you know how? Say something. You got to check the 3 conditions. Keyue, what is the first condition? You have to find the value of the function at and hoping that it exists and well defined. What's the next thing that you need to check? The limit.
exists.
So clear you watch the video now. And after that you doze off, right? I know it's not very exciting.
The one is the
And
limit
thirdly,
equals to
right,
F0.
you just have checked these three conditions. Right, and then it's done here, okay?
It's not, it's F0.
Ah. Thank you. Right, so the way to do the checking is given there. So we have to check whether or not it satisfies the condition of continuity on a closed interval. What's the next lesson? B. Okay. Okay, so you have done the part A, we will finish here. And then we will catch up again on Monday, right? Monday. Okay, with example 33A, we will end the class. Okay, class is dismissed. Goodbye, class.